All right, let's get you exam ready. This is your rapid-fire revision on a massive topic for your GCSE Physics exam, the electromagnetic spectrum. In just the next few minutes, we're going to make sure you have this topic absolutely nailed. Okay, let's dive right in with a question. Think about it. What on earth connects your phone getting a signal, a hospital taking an X-ray, and you feeling the warmth of the sun? They seem completely unrelated, don't they? Well, turns out they're all part of the same incredible family, all linked by one fundamental concept in physics. So here's our game plan. We're going to start with the absolute basics. Then we'll take a tour of the whole spectrum. After that, we'll cover the really important properties and dangers, look at how we use them in the real world, and finish up with the absolute must-know facts for your exam. Let's do this. Right, first things first, let's build a solid foundation. What are we actually talking about when we say electromagnetic waves? Here is the core definition you've got to know. Electromagnetic, or EM waves, are all about moving energy from one place to another. They're a type of wave called a transverse wave, and their job is to get energy from a source, like a radio transmitter, to an absorber, like the aerial on your radio. Simple as that. It's just energy on the move. And what does transverse even mean? Well, you know how with sound waves, the vibrations go back and forth in the same direction the energy is traveling? Transverse waves are different. Their vibrations, or oscillations, are at a right angle. They go up and down while the energy moves forward. Think of a ripple on a pond. And the crucial thing to remember is that all EM waves are transverse. Every single one. Okay, time for the grand tour, and trust me, you're going to want a way to remember the order of the spectrum. I've got a great mnemonic for you. Real monkeys in velvet underwear excite gorillas. That's radio, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Say it a few times, it'll stick. And here is the whole family all lined up. Over on the left, we've got radio waves with their really long wavelengths and low frequency. But as we move across to the right, you can see the wavelength gets shorter and shorter, and the frequency gets higher and higher. This relationship is a super important takeaway. As the wavelength goes down, the frequency goes up. It's kind of like skipping ropes. Long, slow ones for the long waves, and short, fast ones for the high-frequency waves. Kicking off our tour, we have radio waves. These are the absolute workhorses of broadcasting, bringing us our TV and radio. Next door, we have microwaves. You probably know them from the kitchen, but they're also vital for satellite communications, mainly because they can pass right through the Earth's atmosphere to get into space. Moving on, we get to infrared radiation. You know this one already. It's what we feel as heat. It's used in heaters, grills, and those cool infrared cameras that let you see in the dark. And then we hit visible light. And what's amazing is that it's just this tiny, tiny sliver of the whole spectrum, but it's the only part our eyes can actually detect. It's also the key to our super fast fiber optic broadband. Now, this is where things get a bit more interesting, and also a bit more dangerous. We're now in the high energy half of the spectrum. Ultraviolet, or UV, is useful stuff. It's in energy-efficient lamps, and it's what gives you a suntan. But this is also where the hazards really start. Too much UV exposure can damage your skin cells, which can lead to premature aging and, more seriously, an increased risk of skin cancer. And at the very end of our tour, we have the heavy hitters, X-rays and gamma rays. They've got the shortest wavelengths and the highest frequencies, which means they pack a serious punch. They're both what we call ionizing radiation, which means they've got enough energy to literally knock electrons off of atoms. It's this power that makes them amazing for things like medical imaging and treating cancer, but it's also what makes them dangerous, as they can cause genes to mutate. So, we've met the whole family. Now let's really zero in on the key properties and dangers. This is prime exam material, so make sure you're paying close attention here. Okay, higher tier students, this one's specifically for you. Refraction. It's what happens when an EM wave, like light, goes from one substance into another, like from air into glass. When it does that, it actually changes speed. And because it changes speed, it also changes direction. It bends. It's all about the wave's velocity being different in different materials. Let's just quickly nail down these hazards. Basically, from UV upwards, the waves carry enough energy to be dangerous. UV radiation damages the surface, your skin. But X-rays and gamma rays are even more of a worry because they're ionizing and can penetrate right into the body, which means they could potentially cause mutations and cancer much deeper inside. So, how do we keep track of this risk? We use something called radiation dose. Now, the official unit is the sievert, but the good news is you don't need to memorize that for the exam. Just understand the concept. It's simply a way of measuring the potential harm to your body from being exposed to this radiation. Okay, enough about the dangers. Let's talk about all the clever ways we actually use all these different waves. Their unique properties make each of them perfect for very specific jobs. Right, this slide is basically your new best friend for revision. It links each wave directly to its use. For you higher tier students, you also need to be able to explain why it's suitable. So for example, radio waves are perfect for broadcasting because their super long wavelength means they can travel for miles and miles without being stopped. And X-rays, they're brilliant for looking at bones because they go straight through soft stuff like muscle but get absorbed by dense things like bone. We are on the home stretch now. Let's lock in these final, absolutely crucial facts that examiners love to ask about. This is a big one, a really, really big one. If you only remember one thing, make it this. In a vacuum, like in outer space, all of the EM waves, from the longest radio waves to the shortest gamma rays, travel at the exact same mind-boggling speed, the speed of light. Their frequency and wavelength are totally different, but their speed in a vacuum is always the same. And finally, where do these waves actually come from? Well, gamma rays are born from changes happening deep inside the nucleus of an atom. And for you higher tier students, you also need to know that radio waves are made by wiggling electrons around in electrical circuits. And what's really neat is that process works in reverse. When an aerial absorbs radio waves, it creates a tiny alternating current inside it that has the exact same frequency as the wave. So, there you have it. From radio waves carrying our favorite tunes to gamma rays fighting cancer, the EM spectrum is absolutely everywhere, and it shapes our world. We've gone through the key properties, uses, and dangers you need for that exam. Now it's over to you. Good luck, and thanks for joining me.